Hello, and welcome to my videos for Euclid's elements. The main references I'm going to use are listed here. First one is based on Heiberg's Greek text and translated with modern English. The purpose of Heiberg's text is trying to make it as original as possible while maintaining a clear mathematical argument. Our last video mentioned that Euclid's element has been extensively studied over the last 2300 plus years. So there are many versions as well as comments for this book. It is probably impossible to be exact the same as Euclid's original text, but we do consider Heiberg's version is equivalent to the original. The second book, on the other hand, provides very detailed information around Euclid's elements. You will find which mathematician commented or revised on which proposition, as well as historical development, comments, and criticism throughout history on each definition, postulate, common notions, and proposition. The main purpose for this book is to provide a different as well as modern perspective of geometry. I will definitely include these discussions in my video. To be honest, this will be my first time to read the entire book in detail. I only read some of the famous propositions and their discussions before, but I never read the whole series in detail. So these videos are more like my own notes or to record my process of reading this book. And I'm sure I will make many mistakes, so feel free to leave a comment when you notice one. Now let's start from Book 1, Fundamental Propositions of Plane Geometry. As we mentioned before, the most important contribution of Euclid's elements is starting from the basic definitions, postulate, and common notions, then arrange previous mathematicians' work in a logical manner. So in this video, we start from these foundations. First, definition. And there are 23 of them in Book 1. Before we jump into the detail, let's think, why Euclid start from definition? Or we can say, why definition is important? Well, when you buy clothes from different brands, do you ever have any experience when you need a size small from one brand, but maybe a size middle from the other brand? Or when you discovered a completely new brand, you probably want to try in person or check the size chart, where you can see the detailed measurements in centimeters or inches. How come we know we can trust a size chart, but not sizes like a small, medium, or large? The reason is that inch or centimeter are clearly defined units. We know exactly how long 1 inch or 1 centimeter is. However, a size small or medium are not clearly defined. Each company probably has its own definition by various reasons. So math, as being a precise language, requires a clear definition of each terminology it uses. You may think that it is not necessary or it is some redundant work. But many times, the confusion are coming from something we call obvious. Now let's see what Euclid defined in his first book. 1. A point of which there is no part. This means that Euclid considers a point is an indivisible location, not a body or has no weight. Like now in time, beginning or end. 2. A line is a length without breadth. Basically, this means that line has only one dimension, length. However, Euclid didn't define what is length or breadth. For clarification, we can use Aristotle's definition as an example. Aristotle defines up and down is length, right and left is breadth, before and behind is depth. Another issue for this definition is that Euclid didn't mention if there are different types of lines. He did mention straight line in later texts. And the circumference of a circle is also a line, which are clearly two different types. 3. The extremities of a line are points. This one shows the connection between points and lines. And the good perspective is that Euclid did define each term, point and line, before talking about their relationship. However, he didn't mention how many extremities can a line has, or what does extremity mean. Intuitively, we may think like this. A line, and then those means extremity. However, consider a circumference of a circle. There isn't any beginning or end. In addition, there are other relationships between points and line. For example, you have two lines, and when they intersect, they also intersect at a point. Modern perspectives prefer using connections like this one, and as for extremity, we can consider it as limit. If you're not familiar with the math definition of limit, don't worry about that. The most important message here is that Euclid intended to define every geometrical object before using them. 4. A straight line is any one which lies evenly with points on itself. Well, as we discussed earlier, this definition indicates that a straight line is just one of the types of a line. But the language of this definition is quite confusing. One of the comments, and here I quote, Euclid wished to express was that of a line which presents the same shape at and relatively to all points on it, without any irregular or unsymmetrical feature distinguishing one part or side of it from another. There are many discussions on this definition, and many famous mathematicians tried to give their own version of this definition, but they all like an explanation, not a definition. Modern geometry probably prefers something like any two distinct points completely determine a straight line, which is a similar saying like definition 3. 5. And a surface is that which has length and breadth only. So similar to definition 2, surface is a two-dimensional figure. Classification of surface is also missing here, where we probably can think of a shape like cone or cylinder, which consists with a plane surface and a curved surface. 6. And the extremities of a surface are lines. So similar to definition 3, here's the connection between surfaces and lines. 7. A plane surface is any one which lies evenly with the straight lines. Well, we've seen similar before. First, plane surface is just one type of the surfaces, and Euclid used similar wording as he defined straight lines. And a modern geometry probably say something like, any straight non-collinear points completely determine a plane. Now we're moving on to the idea of angle. 8. And a plane angle is the inclination of the lines to one another, when two lines in a plane meet one another and are not lying in a straight line. 9. And when the lines containing the angles are straight, then the angle is called rectilinear. Euclid classified angles by whether an angle is formed by straight lines, even though there is only one proposition in Book 3 used that angle not formed by straight lines. 10. When a straight line stood up on another straight line, makes adjacent angles, which are equal to another. Each one of the equal angles is a right angle, and the former straight line is called a perpendicular to that upon which it stands. 11. An obtuse angle is one greater than a right angle. 12. An acute angle is one less than a right angle. What we see here is a definition of right angle, as well as perpendicular, but only from one direction, meaning one line is perpendicular to the other, but not the other way around. We will prove that later. For the obtuse and acute angle, people criticize that Euclid didn't mention that they should be formed by straight lines. Modern geometry usually uses the idea of 90 degree or pi/2 in radian for a right angle. However, such angle measurement doesn't exist at that time. The only exact known angle measurement is a right angle, so right angle is their unit. For example, instead of saying the sum of all three interior angles of a triangle equals to 180 degrees, You will say the sum of all three interior angles of a triangle is 2 right angles. For the next part, we're going to move on figures, or using the word shape to be more appropriate. 13. A boundary is that which is the extremity of something. And 14. A figure is that which is contained by some boundary or boundaries. 15. A circle is a plane figure contained by a single line, which is called a circumference, such that all of the straight lines radiating towards the circumference from one point amongst those lying inside the figure are all equal to one another. 16. And the point is called the center of the circle. Let's first talk about the differences between the square bracket and round parentheses. Heiberg added the words in square bracket in his Greek version, probably because the next two definitions just use the word circumference without any explanation. Richard added those in round parentheses when he translated in English to make it more smooth. The definition here is only explained that what does the word circle mean, but doesn't provide any information about the existence of circle, or if it exists, how to construct it. Such information is provided in Postulate. And this definition is also very close to modern geometry definition of a circle, which is a set of all points that have the same distance to a fixed point. 17. And a diameter of a circle is any straight line being drawn through the center and terminated in each direction by the circumference of the circle, and any such straight line also cuts the circle in half. For the last part, that diameter cuts the circle in half, which sounds more like a postulate or theorem other than a definition. Proclus also mentioned that Thales was the first to prove this. 18. And a semicircle is the figure contained by the diameter and the circumference cut off by it, and the center of the semicircle is the same point as the center of the circle. It seems like commentators use this definition to classify figures in two ways. First, we can consider the location of the center, which can be classified some figures like circle, where the center located within the figure, semicircle, the center located on the perimeter of a semicircle, outside the figure, probably like a single-branched hyperbola. The second way of classification can be considered as a figure bounded by how many lines? By one line, a circle. By two lines, semicircle. 3 lines, a triangle, for instance. 19. Rectilinear figures are those figures contained by straight lines. Trilateral figures being those contained by 3 straight lines, quadrilateral by 4, and multilateral by more than 4. 20. And of the trilateral figure, an equilateral triangle is that having 3 equal sides, an isosceles triangle that having only 2 equal sides, and a scaling triangle that having 3 unequal sides. 21. And further of the trilateral figures, a right-angled triangle is having a right angle, an obtuse angle triangle than having an obtuse angle, and an acute angle triangle than having 3 acute angles. These definitions are very similar to our today's definition. Probably we just add some other words like pentagon, hexagon, as well as polygon, for example. 22. And of the quadrilateral figures. A square is that which is right-angled and equilateral. A rectangle that which is right-angled but not equilateral. A rhombus that which is equilateral but not right-angled. And a rhomboid that having opposite sides and angles equal to one another, which is neither right-angled or equilateral. And let quadrilateral figures besides this be called trapezia. It seems like Euclid just lists out different types of quadrilateral due to previous work, and himself only focused on squares in the book. You may also notice that we're missing parallelogram here. The reason is that there isn't any definition for parallel line yet, which is going to be our next one. 23. Parallel lines are straight lines, which being in the same plane and being produced to infinity in each direction, meet with one another in neither. There are a lot of discussion on how to define parallel lines. First, same as Euclid's definition, but mathematicians like Gauss argue that we cannot really observe infinity. Second, by corresponding angles are equal one with transversal. Third, by equal distance between two straight lines. Well, modern geometry still prefer Euclid's definition, I think, or at least that's the definition how I learned it. Okay, now we're done with the 23 definitions. Next part is postulate. Postulate 1. To draw a straight line from any point to any point. This short postulate actually includes many inferred information. First, the existence of points. Second, the existence of distinct points. 3. The existence of straight line. 4. The uniqueness of the straight line between two points. Many people argued that this should be listed, while others think there's enough implication. 2. And to produce a finite straight line continuously in a straight line. Or we can rephrase this as two straight lines cannot have a common segment. Many mathematicians try to prove so, but at the end agreed to make this uniqueness as a postulate. 3. And to draw a circle with any center and a radius. It seems like the original text version used the word distance other than radius, since Greek doesn't really have a corresponding word of radius. We're going to use radius here just for our own convenience. 4. And that all right angles are equal to one another. Well, this postulate tells us that a right angle is a terminate magnitude, which form the basis of angle measurement. This can also be considered as invariability of a figure, which some commentators thought this should be a theorem that need a proof, include David Hilbert, who gave a proof in his book Foundations of Geometry. And now, the famous postulate 5. And that if a straight line falling across two other straight lines makes internal angles on the same side of itself, whose sum is less than two right angles, then the two other straight lines being produced to infinity meet on that side of the original straight line, that the sum of the internal angles is less than two right angles, and do not meet on the other side. Okay, this is very complicated, so let's draw a figure to illustrate. So they said if there is a straight line falling across two other straight lines. So let's say two straight lines. Then this is the line falling across the two other straight lines. And then they make the internal angles on the same side of the straight line, which is this two. And it said if the sum of these two angles is less than two right angles, then if we extended these two lines, they will intersect, and they only intersect on the side where those two angles are, not to the other side. This postulate got a lot of discussion from the very beginning, that this one should be a theorem, and a proof is needed. Well, you can see this is really long compared to the previous 4 postulates. However, here's the story. I quote this passage from his book. When we consider the countless successive attempts made through more than 20 centuries to prove this postulate, many of them by geometers of ability, we cannot but admire the genius of the man who concluded that such a hypothesis which he found necessary to the validity of his whole system of geometry, was really indemonstrable. Until the early 19th century, Gauss, who first expressed the idea that this postulate cannot be proved, and laid the foundation of a new branch in geometry, non-Euclidean geometry. The following mathematicians also had a great contribution: Schrickert, Torinus, Lobachevsky, Bollier, and Riemann. And then next, we move on to the common notions. First, things equal to the same thing are also equal to one another. And if equal things are added to equal things, then the wholes are equal too. 3. And if equal things are subtracted from equal things, then the remainders are equal. 4. And things coinciding with one another are equal to one another. 5. And the whole is greater than the part. People argue that Euclid actually used more common notions than he listed here. We're going to talk about this when we're showing the proof of his propositions. Thank you very much for watching.